Beyond our planet, at a distance of billions of kilometers, lie unexplored realms. Space is the greatest mystery humanity has ever tried to solve. And among its enigmas, black holes hold a special place. Absorbing light, time, and space that cannot be seen directly, but their influence is felt everywhere. What are black holes? Why do they frighten and captivate scientists and poets alike? And most importantly, could they one day consume everything we know, the entire universe? Our film is a journey to the frontiers of modern science. We will peer into the heart of a black hole, listen to astrophysicists' insights, embark on a mental voyage across the universe, and try to understand, do we have a chance to escape the fate dictated by these cosmic monsters? In the beginning, there was a super-dense incandescent cloud of matter. It exploded in the Big Bang, giving birth to space and time. Billions of years later, the first stars, galaxies, and then black holes began to form in the universe. When a massive star exhausts its fuel, it can no longer support its own weight. Gravity takes over, the core collapses, the outer layers disperse, and what's left compresses into a point of infinite density, a singularity. This is how a black hole is born. A black hole is not just a bottomless pit. It's a laboratory for testing the limits of our knowledge about the nature of space, time, and matter. Everything that falls in disappears from our universe, or perhaps continues to exist, but in another form. But can these giants grow endlessly? Can they devour not only nearby stars, but entire galaxies? And if so, where is the limit? We will explore what we currently know about black holes and try to answer the main question: can their power plunge the universe into darkness? Gravitational monsters. That's how black holes are often described. But today, they're no longer just a hypothesis, but observable objects. We see stars orbiting what seems to be an invisible center. We detect gravitational waves, the ripples in space-time caused by the merging of black holes, first observed in 2015 by LIGO. With the most powerful telescopes, including the Event Horizon Telescope, humanity has seen the shadow of a black hole, the silhouette of the event horizon around the supermassive black hole in the galaxy M87. It was a landmark confirmation of Einstein's general theory of relativity under extreme conditions.
The event horizon is a boundary beyond which nothing, not even light, can escape. Everything that crosses it becomes part of the black hole. We don't know what happens next. Perhaps it's a gateway to another universe?
There are different types of black holes. Stellar mass black holes form from collapsing stars and usually weigh between 5 and 50 times the mass of our sun. Supermassive black holes, found in the centers of galaxies, can have masses equivalent to billions of suns. In between, we have intermediate mass black holes, rare and still under investigation. Black holes grow by absorbing matter from their surroundings, forming an accretion disk that emits intense X-rays as particles spiral inward. These emissions are a primary method by which we detect black holes indirectly. Another method of detection is gravitational lensing. When the black hole's immense gravity bends light from background objects, creating arcs and rings of distorted images. This confirms their mass and gravitational influence. Even black holes are not eternal. According to Stephen Hawking, they slowly evaporate by emitting what we now call Hawking radiation. This quantum mechanical process implies that black holes lose mass over astronomical timescales, eventually vanishing completely. At the centers of galaxies lie supermassive black holes, such as Sagittarius A star in the Milky Way. Their origin is still debated. Some theories suggest direct collapse from massive primordial gas clouds, while others argue for a slow growth from smaller black holes via accretion and mergers over billions of years. What if such giants keep growing? Could they consume their entire galaxy? Currently, feedback mechanisms, such as energy outflows from active galactic nuclei, appear to regulate growth. But if those mechanisms fail, the balance could tip. Beyond their mass and invisibility, black holes vary in complexity and behavior. Most real black holes are not perfectly static, but rotate. These are called Kerr black holes, named after Roy Kerr, who first solved Einstein's equations for a rotating black hole in 1963. Kerr black holes drag space-time around with them, an effect known as frame dragging. This rotation can lead to the formation of a region outside the event horizon called the ergosphere. In this zone, particles and even light are compelled to move in the direction of the rotation. Some energy can theoretically be extracted from this region, known as the Penrose process. Many supermassive black holes are also classified as active, especially those powering quasars. Quasars are extremely bright galactic nuclei, visible from billions of light years away, where matter falling into a supermassive black hole emits vast amounts of energy. These objects helped astronomers discover black holes long before direct imaging was possible. Another mysterious concept in theoretical physics is the naked singularity, a hypothetical point of infinite density not hidden by an event horizon. If such objects exist, they could violate the cosmic censorship conjecture and expose the raw core of gravitational physics to observation. So far, no such singularities have been found.
If naked singularities exist, they could offer unprecedented access to quantum gravity, perhaps the key to unifying general relativity in quantum mechanics.
This growing knowledge continually reshapes our understanding of the universe. Black holes are no longer just the end of stars. They might be central to galaxy formation, cosmology, and the ultimate fate of space-time itself. Let's consider hypothetical scenarios for the distant future of the universe in which black holes could determine the ultimate fate of everything we know. Could black holes consume the entire universe? Imagine, billions of years from now, stars are dying out. Matter becomes sparse. The universe turns cold and empty. In this darkness, black holes remain, the remnants of former energy and light.
There's a theory of the heat death of the universe. Everything slowly approaches thermodynamic equilibrium. Only black holes will be left. They too will slowly evaporate, and nothing will remain.
The Big Freeze, heat death, the most widely accepted scenario. As the universe continues expanding, galaxies drift apart, stars burn out, and entropy increases. Eventually, only cold remnants like white dwarfs, neutron stars, and black holes remain. Over trillions of years, even black holes evaporate via Hawking radiation. The Big Crunch. If the density of the universe is high enough, gravity might reverse the expansion. Galaxies collapse back together, stars ignite again, and black holes merge. Ultimately, everything might contract into a final singularity, mirroring the conditions of the Big Bang. The Big Rip. If dark energy continues accelerating the expansion of the universe at an increasing rate, it could eventually overcome all other forces. First galaxies, then stars, planets, and even atoms would be torn apart. Black holes would evaporate or be stretched into nothingness. Each scenario depends on the exact properties of dark energy, the total mass energy content of the universe, and the nature of gravity at cosmological scales. But what if the end is not truly an end? Some physicists propose cyclical cosmology, where the universe undergoes infinite cycles of expansion and contraction, a cosmic heartbeat. Others suggest a multiverse, where black holes might spawn new universes with different physical constants, as in the cosmological natural selection theory.
Some quantum gravity models propose that a singularity inside a black hole could bounce and generate a new Big Bang. In that case, black holes may not end everything. They may begin something else entirely.
Could our universe have been born from such a process? These ideas, though speculative, reveal how black holes are no longer just cosmic vacuum cleaners. They might be fundamental to the life cycle of the cosmos itself. From the dawn of time, humans have looked up at the sky. In those stars, we saw gods, myths, and dreams. Today, we see galaxies, supernovae, and black holes. And yet, the questions remain the same. Where did we come from? Where are we going? Is there an ultimate end to all things? Confronting the vastness of the cosmos and the idea of a finite universe evokes awe, but also existential fear. It challenges our place and purpose. But this awareness is what makes us extraordinary. We are made of the same elements forged in stars, and we have the capacity to understand the laws that govern them. Black holes, entropy, cosmic expansion, all are part of a grand narrative, one that we, as sentient beings, are uniquely able to explore. It's not just about survival, it's about meaning. Our desire to understand, to ask questions, to peer into the void is perhaps the greatest expression of what it means to be human. The universe may not care about us, but we care about it. We observe, we study, we wonder. And in doing so, we give the cosmos a voice.